So let us begin this lecture. Okay. So we are now going to prove very important theorem in field theory. That is actually the fundamental theorem of Galois theory. The fundamental theorem of Galois theory that we are going to prove. So, but before proving the fundamental theorem of Galois theory, we need some basic stuff to be constructed. Okay. So let us start with some basic results. We start with the definition. So a definition. So we defined a special type of function from a group to a multiplicative group to a field, and we call that function as a character. Okay, so a character of a group G with values in a field L with values. So character we denoted by chi. So a character chi of a group G with values in a field L is a homomorphism is a homomorphism from G to the multiplicative group of L, because the non-zero elements of group are this field L and the multiplication is a group. So to be precise, what is this chi? This chi is actually a mapping from a group G to the multiplicative group of this field L, such that so it is a group homomorphism. So chi of G1 G2 has to be same as chi chi of G1 times chi of G2. Okay, for all G1 G2 in G. Okay, and chi of G is non-zero because this L cross has no zero element, so therefore, and chi of G is non-zero element of L for all G in G. So this chi is a mapping from G to L cross such that chi of G1 G2 is chi G1 chi G2, and chi G is non-zero for all elements for all non-zero element of L for all G in G. If this condition is satisfied by this function chi, so we call this chi as a character of the group G with values in the field L. Okay, and these characters, they are set they are said to be linearly independent if the following condition is satisfied. So let me define it properly. So the characters the characters chi1, chi2, so on, chi n of G are said to be linearly independent or said to be linearly independent if they are linearly independent as functions on G. If they are linearly independent as functions of G, as functions on G. That is to say that if if there is no non-trivial relation, no non-trivial relation, non-trivial relation, uh, a1 chi1 plus a2 chi2 plus so on plus an chi n equal to 0. Okay, so linearly independent means there is no non-trivial relation of this type where, so these a1 a2 so on an, they are elements of L, not all 0, not all 0. Okay, so let us call this relation as star. So there is no non-trivial relation of this type means what? Means this this type of non-trivial relation should not be true um, for every element of the group, in fact. So you can say that a1 chi1 of G plus a2 chi2 of G plus so on plus an chi n of G is equal to 0 for all G in G. Okay, so we have defined two things. We first defined character of a group G with values in a field L. It is just a homomorphism from a group to the multiplicative group of the field. Or you can say that it has the properties that chi of G1 G2 is chi G1 chi G2 for all G1 G2 in G, and chi G is non-zero element of L for all G in G. Okay, this is the definition of a character, and these characters are said to be mm, linearly independent if there is no non-trivial relation of this form that is satisfied. Means the only relation that is satisfied is the trivial relation. Okay, so now we are actually going to prove that the distinct characters of a group with values in a field, they are actually linearly independent. This is what our claim is in the next proposition, a theorem. So we have this theorem. If 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 chi1, chi2 up to so on chi n are distinct characters of G, or distinct characters of G with values in a field L, with values in a field L, then they are linearly independent over L. Then they are linearly independent over L. Independent over L. Okay. So let us see the proof. It is just a straightforward proof. Suppose on contrary that they were linearly dependent. Suppose on contrary that these were linearly dependent. These were linearly dependent. Okay. So this means what? This means if they are linearly dependent, uh, it means there were non-trivial relations of the type star. There were non-trivial relations of the type star. So among all the non-trivial relations of the type star, choose one with minimal number of non-zero coefficients. So all the non among all the non-zero, or you can say linear dependence relation, linear dependence relations star above, choose one with minimal number, choose one with minimal number of non-zero coefficients, non-zero coefficients, and this can be done. Say say there are m number of AIs which are non-zero. So say there are m number of AIs which are minimal and non-zero, which are non-zero. Okay, that, and you can say that without loss, you can say that they are without loss. Let those be A1, A2, so on, AM. So the relation star now becomes A1 chi1 plus A2 chi2 plus so on plus AM chi m equal to 0, where all of these AIs, they are not 0. So then for any G in G we have then for any G in G, we have uh, A1 chi1 G plus A2 chi2 G plus so on plus AM chi mg equal to 0. Okay, so say this equation is double star. Now since they are distinct, so let G naught be an element be in G with chi1 of G naught is not equal to chi m of G naught, and this is possible because they are distinct. These characters are chosen to be distinct, which exists as chi1 is not equal to chi m. Now since this double star holds for each G in G, so in particular it also holds for the element if we take G naught G. Now since the equation double star holds for every element of G, for every element of G, so in particular it holds for this element G naught G, which is also an element of G. Okay, so then what happens? So this means A1 chi1 of G naught G plus A2 chi2 of G naught G plus so on plus an chi n of G naught G, this is 0, and these chi i's, they are actually characters, so they are homomorphism. So this means A1 chi1 G naught chi1 G plus A2 chi2 G naught chi2 G plus so on plus an chi n G naught chi n G, this is 0. Okay, so let us call this equation as 3 star. Now multiplying multiplying equation double star by chi m g naught and subtracting from this triple star and subtracting from the equation triple star, we get an equation of this form. So you would just see it, it is chi m G naught minus chi 1 G naught of A1 chi 1 G, this is the first term, plus second term would be chi m G naught minus chi 2 G naught of a to chi to g plus so on, the last term, mth term would cancel out, and you will have this this as last term chi m g naught minus chi m minus 1 g naught am minus 1 chi chi m minus 1 g equal to 0 for all g in g. So what does it mean? It
सर
means
सर वहाँ ऊपर वाली इक्वेशन में काय एम है ना?
कहाँ पे?
सर पहली इक्वेशन आप देखिए जो स्क्रीन पे है, सर पहली और
Oh
दूसरी.
yes, you're true. It is chi m. Yes, I'm wrong. It is am chi m, और ये भी actually am chi m है. Good. Okay, so what you get here? Here the first coefficient is non-zero because we have chi m of g0 is different from chi 1 of g0. So this coefficient is at least non-zero. But this is an equation with m minus 1 non-zero coefficients. Okay, which is a contradiction because we are assuming that this is the minimal number of non-zero coefficients such that such a relation is satisfied. But here you are getting that there are m minus 1 non-zero coefficients in a relation, linear dependence relation of this form is satisfied, which actually contradicts. So here the first coefficient is non-zero. Here this is non-zero. So this is the relation. In fact, linear dependence relation, you can say linear dependence relation. So this is a linear dependence relation with fewer non-zero coefficients. With fewer non-zero coefficients. Fewer non-zero coefficients. A contradiction to the minimality of this equation. So our assumption is wrong. So a contradiction. So therefore these characters are linearly distinct, characters are linearly independent. Okay. So यहाँ भी आप इसको m कर लें. If chi1 chi2 so on chi m statement में भी. So there are, we have chosen m number of these. No, ये तो n ही है, ये n ही रहेंगे. यहाँ हमने जब मिनिमल लिया तो ये m हो गए. ओके, सो इट्स 2, ये n ही होगा. Is it clear? So distinct characters are linearly independent. And as a remark, if you take injective homomorphisms of a field to a multiplicative group of some other fields, then they are also going to be linearly independent. In particular, you will say that distinct automorphisms are linearly independent. Uh, so now if we consider an injective homomorphism, if we consider an injective homomorphism, say sigma of a field K into a field L, into a field L. usually called these injective homomorphisms, they are called as embeddings, called an embedding of K into L, embedding of K into L. Then in particular sigma is a homomorphism. In particular, sigma is a homomorphism from the multiplicative group of K to the multiplicative group of L, is a homomorphism from G equals to the multiplicative group of K into the multiplicative group, say G dash of this L. And because it is injective and it maps 0 to 0. Being a homomorphism, it maps 0 to 0. Okay, so you can view this sigma as a character of this is because sigma is injective and sigma of 0 is 0. So you can view this sigma as a character of the multiple, this G, character of G into this L. So sigma can be viewed as a character of G into the field L. Okay. So this means what? This means if I take distinct embeddings of this type, then by previous theorem they are linearly independent as functions on K. And in particular, because automorphisms are by definition injective homomorphisms, so they are also going to be linearly independent as functions on K. So what I conclude from this remark and the previous uh, theorem is this corollary. So it says that if sigma 1, sigma 2, so on, sigma n are distinct embeddings, of a field K, of a field K into a field L, then they are linearly independent as functions on K. Then they are linearly independent as functions on K. And in particular, distinct automorphisms of K are linearly independent as functions on K. In particular, distinct automorphisms of K are linearly independent as functions of K, as functions on K. So this is very important conclusion, because we came to know a very important thing about automorphisms, that they are actually distinct automorphisms. They are linearly independent as functions on K, and this would help us in our future results. Okay. Oh, so we use this corollary to prove now the fundamental relation between the orders of subgroups of the automorphism group of a field K and the degree of extension of their fixed fields. Okay. So we now use this corollary to prove the fundamental relation between the orders of between the orders of subgroups of the automorphism group, orders of subgroups of the automorphism group of a field K, of a field K, fixing fixing a field F, fixing a subfield F, and the degree of extensions and degree of their extensions. In fact, we show that they are same, and their degree of extension. We actually seen this in with the help of example we have seen in our, if you remember your last lecture. So we chosen this q root 2 root 3 as an extension of q. Okay. We considered this group out of this q root 2 root 3 q. So we have seen that this group has order 4, and we have also noticed that we know that degree of extension of q root 3 root q root 2 root 3 over q is also 4. Okay, so we have seen that this group is actually a Killing 4 group, K4 group. We considered its subgroups, and we also considered the subfields of this field, which are fixing q. So we seen that those fields are q root 2, q root 3, q root 6. We also considered the subgroups of this K4 corresponding to this field, and this field. You remember in the last lecture. But now we are going to prove a general result. Okay. So I think we will rejoin to just uh, to prove the main theorem, because in between it would get disconnected, and we will have lot of equations that we will use. So it will be difficult to recall those equations. So let us rejoin.